Hello everyone, this is Dr. Young, and in this video I'm just going to introduce energy to you, kind of what it is, and we'll talk about the units that we use for energy and the two main types of energy that we're going to talk about for our class. So definition for energy, it's kind of a weird nebulous concept, like we kind of like get that there's energy, but like how do you define it? And the definition that I like the most is basically the capacity to transfer heat or do work. That's what energy is. If something can transfer heat, it's got energy. If it can do work, it's got energy. And so we're gonna look at these two different pieces here, right? So transfer heat, where heat just means that it causes a change in temperature. Causes a change in temperature. And we're gonna see this, I'll say temperature or bonding. In the future, we're gonna also see it cause changes in bonding, like melting and boiling or even chemical reactions. And the abbreviation for heat is Q. That's what this Q is right here. This is the Q for heat. Why is it Q? I'm not sure. I could probably look it up, but I'm not going to. And then we have work, right? Or the ability to do work. And work, which is abbreviated as a W, which makes a lot of sense, is just basically that it moves an object, right? The ability to move an object. Ability to move an object. In chemistry, this is PV work. It's something called PV work, which is basically like the expansion of a gas or something like that, right? It might be work. Like imagine like a piston in a car where the gas expands and moves the piston. This equation right here is one that we're going to come over. We're going to see again and again and again. Energy, so E stands for energy, equals the heat plus the work, right? So if you're going to have a change in energy, it's going to be due to something being worked on or something being heated, right? Either gaining heat or losing heat. So what are the units of energy? There's two main ones that you're going to see. You're going to see calories, which is abbreviated as a small CAL, or you're going to see joules, which is abbreviated as a large J, a capital J. A calorie is just the amount of energy that is required to raise 1 gram of water, 1 degree Celsius, specifically from 14.5 to 15.5 degrees Celsius. That's like the exact definition. And that's just because the amount of energy to change temperatures of things is not like a linear relationship when you get really high. Like if you're gonna change something from being like 831 degrees Celsius to 832 degrees Celsius, that's gonna be a slightly different amount of energy. But regardless, a calorie is the amount of energy required to raise 1 gram of water, 1 degree Celsius. That's the most common one we use. But the idea here is that this is fairly small. This is a small amount of energy. And for us, on our scale, we almost always use kilocalories. We almost use kcals, right? 1,000 of these little calories, just like a kilogram is 1,000 grams or a kilometer is 1,000 meters. So a kilocalorie is probably something that you're going to see more often. A kilocalorie is 1,000, right? This equals 1,000 calories. And you may have heard the term calorie before, especially because you may have eaten before or looked on a container that has the calories written on it. I'm just going to point out right now that the calories on your food container are not the calories that I'm talking about right here. They're related, but they're different. The calorie that we use in chemistry and science is a lowercase c, and that's the amount of energy to raise 1 gram of water, 1 degree Celsius. But a food calorie, is actually written with a capital C. Notice a capital C here, and it's abbreviated with a capital CAL, not a lowercase CAL. And this is the food calorie. So it's actually a kilocalorie. 1 calorie on like a milk carton or something like that is actually 1,000 calories with a little c. So 1 calorie big C is worth 1,000 calories little c. So this is your food calorie. I just wanted to mention that since I'm sure it's the first thing you thought of. So food calories are actually kilocalories. Now, joules is another unit of energy that you're going to see. Either of these types of units are fine for energy. You're going to see them both. Some countries favor one versus the other. Certain books favor one versus the other. I tend to use kilocalories more than I use kilojoules, but regardless. And a joule is just defined as, so let's see, 1 calorie is, well, I put it here, 4.184 joules, right? So that'll be a good conversion factor to know if you have to relate calories to joules. So we talked about kind of like what energy is, right? It's capacity to transfer heat or do work. And here's some units that we're going to see, how many kilocalories or kilojoules are being transferred between two objects. Well, let's talk now about the types of energy, or two of the types of energy that you're likely to see. Now, if you ever had any physics or anything before, either in high school or previous classes, you've certainly heard of potential energy and kinetic energy. And so what I'm going to do is I'm going to kind of compare and contrast how we deal with that in physics versus chemistry, so you can kind of see how they're related but how they're different. So potential energy is just the energy that's stored in an object because of its relative position to something else. In physics, that's done by like, you've got a ball up on a hill, right? It's at a certain height. This axis would be heights, so h for height. And this ball is going to roll down a hill. It's going to roll down a hill to get to some new height. Right, so it's going to go from here down to here. And this would be like before and after, I guess. And that you have this difference here, which is the change in height. Right, so this would be a change in height, delta H, a change in height. And when you're talking about potential energy and like this ball and stuff, right, you'll see in physics they'll use equations like that PE, the potential energy equals the mass of the object times the force of gravity times the height, right? So here would be mass. This is your gravitational constant. And this is height. So you can actually calculate, right? Like if a ball goes from like being 100 feet up to 10 feet up, drops 90 feet, you can calculate how much energy, how much potential energy was lost when it went from 100 feet to 10 feet, right? Just by using this change in energy here. And that would be the potential energy, right? Right, you'd much rather have a rock fall on your head from 1 inch above your head rather than like a mile from above your head, right? There's a huge difference in the amount of energy of a rock 1 inch above you versus a rock, 5,000 feet above you. And so that's talking about the relative position, right? High versus low. And when you go from high versus low, there's a change in your potential energy. Now, the exact same thing is true for chemistry, but we don't have like, balls on hills or anything. What we have is we have the inherent energy in something like hydrogen peroxide, for example. I'll just do H2O2. Right, this is hydrogen peroxide, H2O2, the stuff that you'd go and buy at the drugstore and put on a cut or something like that. And the idea is that H2O2 is higher in energy, so we don't use heights, we use a value of energy, so like stability. So the idea is that this, and let me draw this in black here. What we're saying here is that this H2O2 is higher in energy and therefore less stable. It's not a very stable molecule, right? Which is why we use hydrogen peroxide to clean wounds and why it kind of bubbles and stuff. It's decomposing. And what it's decomposing to is the much more stable water and oxygen gas, which is what's responsible for those bubbles. And when you transform from being hydrogen peroxide to being water, now all of a sudden we're lower in energy. And we are more stable. We went down that hill. We went down in energy. And so it's exactly analogous to the boulder on a hill analogy, right? You can roll a rock downhill, it's going to flow downhill, it's going to roll downhill. Same thing happens in chemistry, right? Different molecules have different energy levels, so they're at different quote-unquote heights when it comes to their stability or how much energy they have. And so for us in chemistry, we do a similar sort of thing, right? You started off up here, you went down to here. This is your change in energy, though, not like a height. This is like how different is your energy. And so for chemical energy, We do things like we say, oh, well, the change in energy during a transformation, right? Melting something, boiling something, something burning, just two reactants, reacting together. What we always say is that, so the delta E always means the final thing minus the initial thing. So this would be the energy at the end, so F for final, minus, I'm sorry, not a delta there, the final energy minus the initial energy, right? Where again, this F just means final, I means initial. So you take the value that you started with and you subtract from the value you end with, and that would be your change in energy. But again, this energy is in relation to the other thing, right? So it's the energy stored in these molecules, but it's compared to where it's going to end up, what it's going to turn into. There are other things that hydrogen peroxide can do other than turn into water and O2. And if it does those other things, it's going to release a different amount of energy because you have a different relative position that you're going to. And so what we're going to do is we're going to start our conversations about this. We'll get way more into enthalpy and reactions and bond making and breaking later. But I just want you to have a general idea that we have this analogy between physics and chemistry where you can be high energy or high on a hill and go down to being low energy or lower on a hill. And that's going to change your relative potential energy, your potential energy basically. And so the other type of energy is kinetic. So let's talk about kinetic. Kinetic energy is just the energy of an object in motion. So when something's moving, it has kinetic energy. If you look at your glass just sitting on your table, we normally, from our frame of reference, wouldn't say that it has a lot of kinetic energy. And I say our frame of reference, right, because obviously the Earth is spinning, the Earth is moving around the sun, our solar system is moving around in the Milky Way is moving through the universe. So it's really, everything's moving, but this is a frame of reference thing. So from a frame of reference, the glass on your table is not going anywhere, or your computer is just got no kinetic energy right now. And in physics, right, it's all about like the rolling ball or something like that, right? The ball rolls down, hits the pins move, they transfer that kinetic energy around. And you have this equation, right, that the kinetic energy, the Ke equals 1/2, and you might remember this from previous videos, but 1/2 of the mass times the velocity, just like the same as speed for us, velocity squared. And in chemistry, we kind of already talked about that. We're like, oh, we got a similar thing, right? We've got molecules that move around. Here I have a gas, right? We've got a bunch of molecules moving around, doing their thing. And so since they're moving, they also have kinetic energy. So we had the same we have almost the same equations for chemistry and physics in this regard, right? We got little particles that are moving around. Again, I did a gas, but even liquids and solids have particles that are jiggling, right? They're always constantly moving. So they always have some kinetic energy. And for us, right, don't forget that we said that this is proportional to temperature, that this equation is proportional to our temp. And so for us, sometimes we refer to kinetic energy as thermal energy. So Ke, kinetic energy, is also known as, aka, thermal energy. It's thermal energy. And those are really the two big types of energy that I wanted to talk about. Those are really the two big types, right? We've got potential energy and we've got the kinetic energy. So what I want to do in future videos is kind of flesh this out a little bit more and start talking more formally about thermodynamics, which in the name itself is talking about how there are changes in heat and what the first and second law of thermodynamics are saying and what a system is versus its surroundings. So that's going to be the idea in the next video. So be sure to watch that. Happy studying.